final presentation of the morning is by Curtis Lauder, and Curtis is a student at Evanston Township High School.
Can you guys hear me? Is it good? Oh, there we go. Thank you. In today's talk, I'm going to talk about the gravitational effect of the asteroid belt on the LISA mission. So in today's talk, I'm going to talk about the purpose and background behind my research, the methodology behind my research, and the results my project yielded. So my research had to do with gravitational waves. Gravitational waves are perturbations in the space-time fabric, as told by general relativity, Einstein. So as you can see in this picture to the right, much like how a stone dropped into a pond will cause ripples to spread across the surface of the pond, two black holes, for example, spinning around each other will cause waves to form in the fabric of space and time. And these waves, as you can see in this animation to the left, cause space to stretch in one direction and to compress in the other, and they travel through from millions and millions of light years away from different events. So in order to detect these waves, we use something called an interferometer. So as you may or may not know, LIGO, which is an Earth-based interferometer, recently discovered gravitational waves. But my research has to do with the LISA project. It's a laser interferometer space antenna. It's a collection of 3 satellites designed to detect the change in distances that gravitational waves will cause as they pass through our solar system. And these changes are on the order of a scale of protons. They're very tiny changes. So there's a worry that as these satellites in space follow Earth in what's called an Earth-trailing orbit, the asteroid belt will actually, the asteroids in the asteroid belt will actually pull on these satellites and cause changes in distance, which might interfere with the results that LISA yields. So to do this, I have to first model the orbits of these asteroids, then I have to estimate their masses, and finally I have to calculate the final gravitational effect. So when I model these orbits, I do it in 2 major parts. I first figure out their 2D planar positions in terms of the orbital plane, that yellow disk there, and then I provide Euclidean transformations using matrices to find their final position. So to do this, I am given a library by the Jet Propulsion Laboratory, their small body orbital elements library, and it contains several parameters that I use to find the actual positions. So what I first do is I have to determine the distance at any given time from the asteroid to the sun, and then I have to figure out the angle across the orbit that this asteroid is in at this specific time. So to start, I'm given this top equation here, and that solves for the mean anomaly. The mean anomaly is simply a number that relates to the angle that the asteroid is in at a given time. So to solve this, I'm given m naught, which is the mean anomaly time equals 0, and that's given by the JPL library. And then to solve for this big T, which is the period, I'm given the second equation here. That's actually Kepler's third law, and since I'm using a sun-based system, I'm able to make the approximation that the period squared is equal to the semi-major axis cubed. So given those values, I can increment time over the course of a year by 5-minute intervals, and I'm able to solve for the mean anomaly of the asteroids at any specific time. So given the mean anomaly, what I have to do next is I have to use this third equation here, and I have to solve for the eccentric anomaly, or the psi symbol there. So the problem is you can't just plug it in and get a value. You have to use what's called an iterative process. So I know that the eccentric anomaly will be some value between 0 and 2 pi. So what I do is I guess that the value is pi, and I get a k value. And based off whether or not the k value is greater than or less than 0, I can iterate towards the right answer, and I get a pretty accurate estimation of what the eccentric anomaly is. So now that I have the eccentric anomaly, I can use this next equation here, and I can solve for the theta, that angle I was talking about before. And so now that I have the angle, I can plug that into this last equation here, and it can solve for that distance or radius of the orbit at that specific time. So now that I have those 2 values, I can perform those 3D transformations, as I talked about before, to determine the position. So I use several different values provided by the JPL library. For example, the longitude of ascending node, argument of periapsis. And what I do is I take the periapsis and I assume it's in the reference direction, that red arrow there, and I use those values to transform that direction into the direction of the final periapsis, and then I do a vector rotation using matrices to find the direction of the celestial body, and then I use the radius I found before to find the actual Cartesian point, the XYZ coordinates of the asteroid at a given time. So next, after I figured out the position of each of these asteroids at a given time, I have to understand their masses. So the difficulty is that we actually don't know many masses. The JPL library I use has over 400,000 plus asteroids, and we know only a handful of their masses. So an estimation of their mass has to be conducted. The way we do this is we use the amount of light that's reflected. So in this top equation here, that H value is called the absolute magnitude, and it relates to the amount of light that we detect at a fixed distance away from the asteroid. So the JPL library gives me that value. However, the next part is I have to randomly assign the types of asteroids. Different types of asteroids, carbonaceous, silicous, metallic, those different types of asteroids have different properties to how they reflect light. So, and we don't know what the types of asteroids from these asteroids are. However, we do know the proportions of these different types in the asteroid belt, so we're able to randomly assign the types to each of these asteroids. And those types give me the albedo, or proportion of light that's reflected off these asteroids, and I'm able to plug that into this top equation here, and that solves for the diameter of these asteroids. And so now that I have an approximation for the diameter, I can use the same random assignment of type I used before to figure out the density, and I can find the mass using those two values. So then when you do that, this is what you get, this picture here. That's a picture of my simulation. Each of those yellow dots are a different asteroid that's done in my simulation. The red circle in the middle there is the sun, and that white dot is a test satellite that I'm taking my calculations towards. So given those values I found before, I'm able to plug in the mass in that equation, and I'm able to use the position of both the test satellite and the position of each of these asteroids to actually find the distance between them. And so using simple Newtonian physics, I can solve the acceleration between each of the asteroids and the test satellite. And then summing those up using vector sums, I'm able to graph those accelerations over time. And these are the net accelerations. So this graph on the left here uses just the albedo mass calculations I showed before, but the graph on the right uses some known masses in there as well. So some important things to notice is that the shapes of these graphs are approximately similar. They follow similar trends. And as well, something to notice is that on the axis here, that you get around 10 to the negative 15, 10 to the negative 14 in terms of acceleration, magnitude of acceleration. But on the graph to the right here, we get around 10 to the negative 12, 10 to the negative 13. The reason for this is because the estimations of masses I showed before tend to underestimate the mass. So for larger objects, the mass is much less than what we'd expect. So so in the graph to the right, we have a larger total mass. So that would increase the magnitude. And so something I noticed when I did my simulation is that I ran with just the top 50 asteroids listed in JPL's library. They're listed by date of discovery. And something important to notice is that they actually get very similar shapes. So this is just using the albedo mass equations before. And if I did the same with some of the known masses in there, and you get the same results. So what this means is that the top 50 asteroids are really representative of the entire population. And as well, something else to notice is that the graphs are actually very smooth. There isn't a lot of noise. So they're very, the changes in acceleration take over the course of days or months instead of minutes. And another thing to notice also is that there's relative periods where the changes of acceleration are mostly constant. And these happen around, for example, here around about 0.4 years. So based off my results, we can make a couple of assumptions about what LISA might experience. The first thing is that LISA will experience smooth effects. So these effects from acceleration will change over the course of a very long period of time. This would be important because gravitational waves, when we detect them, they happen over the course of a couple seconds as opposed to days. And so since we don't have to deal with very fast changes in acceleration, there won't be a lot of disturbance from the asteroid belt in our final calculations. So some future research I could conduct, given my results, is I could calculate the orbits of asteroids near the launch date. The orbits I used were nowhere near the launch date. The launch date is in 2034. It's planned to be 2034. So the purpose of my research wasn't really to determine exactly what the effects were, but just what kind of effects we could expect. So given that, we can also determine more known masses of asteroids. As we approach the launch date, we will undoubtedly discover more masses of asteroids, as well as more asteroids themselves. And so we could add those to my simulation quite easily and find more accurate data. And as well as add comets to my data. So I use just asteroids, and asteroids tend to be very planar with the orbit of the Earth. Comets, on the other hand, are very eccentric, very out-of-the-plane orbits. So we would expect there are probably more disturbances in LISA's results from comets. And then the last thing we could do is model the exact effect on LISA. As I said before, I used just a test satellite. I could use the orbits of the actual LISA satellites and graph those changes in distance that we would expect. So I'd like to thank Professor Shane Larson from Northwestern and Dr. Mark Van Drasik for helping me through my research. And do you have any questions?
I have two. One, because I'm not an astronomer, what is periapsis?
So periapsis is just the lowest point in the orbit. So as orbits are very eccentric, such as here, this point A would be the periapsis, and the point B would be apoapsis, as it's called in high school.
Okay. My second question is, you mentioned that these effects, these gravitational effects, are on the scale of a proton,
Yeah.
right? But then you're estimating the masses of these asteroids, right?
Mm-hmm. Let me explain. We're not actually trying to calculate if these asteroids are creating gravitational waves. That's not what we're calculating. We're calculating the fact that these satellites, they're very far away from each other. So any change in distance we might experience from the gravitational pull of an asteroid might interfere with our ability to detect changes in distance from gravitational waves as they pass through the solar system.
So to sort of follow up on that, since you're looking at a change distance of 10 to the minus 15 meters for the gravitational wave, how big of an asteroid would it take to cause that much of a fluctuation in the position of your satellite?
Right. It's not really about whether or not it makes it provides any acceleration on the asteroid at all. What really matters is whether or not there are very fast changes. So from these graphs I showed before, the changes take place over very, very long times. So the LISA team could be able to better account for those. What matters is whether or not there are very noisy, very interrupted changes in acceleration, which would be very disruptive to data collection. Yeah.
I think the data collection you said was a matter of seconds.
Yeah, so gravitational waves, for example, this is the LIGO data. This happened over the course of a few seconds here. And so we don't really care about whether or not there's changes in acceleration, which would disrupt us over the course of months, because we're really, really looking for over the course of seconds. Yeah?
So your argument is, I understand your argument, which is the kinds of effects you're seeing in the asteroids, which have timescales in thousands of seconds or hundreds of thousands of seconds, are insignificant for the purposes of a gravitational wave experiment where you're looking at interactions that take place over fractions of seconds. My concern would be your way of analyzing this that has given you that time scale of years for the asteroid movements is based on data collection that's being measured in what, months?
No, I iterate my the orbits of asteroids over the course of 5 minutes. That's how I do it.
Okay, so you're within a factor of 100 of the time scale that you're actually trying to
Yeah.